Okay. In the last video, we introduced the idea of the least squares approximation and solving the normal system. So we're going to take this system right here and set him up, and then I actually want to look at a visual of him so that we can see what's going on. So we're going to take the A matrix here, which would be -2, 1, 0, 2, and -1, 3. X is going to be x1, x2, and B is going to be 3, 3, 3. 3 happens to just be my favorite number. And notice that if I do A times X, I will get this right here, N equals B. So this is just another way to write this, AX equals B, where we've got to solve this for X. But if you put this into your calculator and try to RREF, you'll get that it has no solution. Now, one more thing that I want to do, I'm going to look at the A matrix, which is -2, 0, -1 as a column, and 1, 2, 3 as a column. Let me make that 3 look a little better. And I'm going to look at these guys as vectors. I'm going to call this vector 1, and this be vector 2. And as we've seen, tying in what we've learned before, the column space of matrix A is what we can make using scalar multiples of vector 1 plus vector 2. Okay, so a linear combination of vector 1 plus vector 2. So let's look at that using our good friend GeoGebra. Okay, so I've got vector 1, so that's our -2, 0, -1 vector there in orange. We've got our 1, 2, 3 vector in blue. And what they make is this light blue kind of aqua colored plane. And I'll hide the XY plane so you can see this. What we're trying to get at is the B vector, which is this purple vector, this 3, 3, 3 vector, and you can see that it's not in the plane. So what we're looking for is the vector that's closest to the B vector in the plane. And I've already done a little bit of work to set this up, but the vector that's the closest to the purple vector is this black vector. And let's see if I can get this turned just about right. Ooh, come on, maybe. Okay. All right. If I can get this turned just right, you'll see that that is the orthogonal projection of the purple vector onto the aqua plane. That would give me the black vector. And the difference between the vector I really want to make and what I can actually make, the black vector, is this red error vector. And so we're trying to find the vector, the black vector in the plane that makes this error vector the smallest it possibly can be. Okay. All right, so let's go back to our paper and find out how we can solve this system. Well, first thing we need to do is set up the normal system. A transpose AX equals A transpose B. So let's do A transpose. Remember that A is a 3×2 matrix. So A transpose will be a 2×3 matrix times by the A matrix. And we need to multiply that by the X vector. So here's A transpose A X vector equals, and our normal system, we'll do an A transpose again, times the B vector. Oops, let me slide that over here. And the B vector was 3, 3, 3. And what we're going to do is we're going to get a little bit of help from the calculator. You might want to pause the video for a second and put A in your matrix and B column vector in as the B matrix, and then run A transpose AX. Or sorry, well, let's find out what A transpose A is and what A transpose B vector is, and then we'll set up our normal system and solve them. Okay, so go ahead and do that, and we'll be back in just a jiffy. Okay. So hopefully you put that in your calculator and found out that A transpose A is the matrix's rows 5, -5, -5, 14, and A transpose B is the column vector -9, 18. So that tells me that the system A transpose AX equals A transpose B is equivalent to this guy right here, which I could even write as an augmented system, and then RREF. And when I do that, okay, let me slide this up here so we've got a little bit more space. Okay, I believe we get -0.8 and 1. So it tells me that my solution is x1 equals -0.8 and x2 equals 1. All right, so that was our solution. So our x vector, our solution is -0.8 and 1. And what does that tell me? It tells me that to make w, the vector that's the closest to the vector that we wanted to make, and the vector we wanted to make was 3, 3, 3, the closest we can get to that is to use -0.8 of vector 1, which was -2, 0, -1, plus 1 times vector 2, which was 1, 2, 3. And when I do that, that gives me the vector 2.6, 1, I'm sorry, 2.6, 2, and 3.8. Okay, so that's the vector that's the closest. In our picture back here, that was the black vector that we were trying to make that's in the plane that's the closest to the purple vector. And to find the error vector, we just do the B vector that we wanted to make but couldn't make and subtract the vector that we could make to find out what our error is, the difference between those guys. Okay. All right, let's come back to our paper. All right. So noting that this guy are the coefficients for the linear combination to make the W vector that's the closest in the plane that we want to make, we can note that if I do A matrix times my X vector, let's see what happens. So we'll get 1.6 plus 1, which is 2.6, 0 plus 2, which is 2, and 0.8 plus 3, which is 3.8. And as mentioned, that happens to be W vector, the vector in the plane that we can make that's the closest to the desired vector. And remember that our desired vector was 3, 3, 3. That was our original B vector. Okay. And as we mentioned just a second ago, the error is the difference between these, well, the error vector is the difference between these two. So the error vector would be 2.6, 2, and 3.8 minus 3, 3, 3. And so that would give me -0.4, 1, -1, and 0.8. And the error is the magnitude of that error vector, which would be the square root of -0.4 squared plus -1 squared plus 0.8 squared. And let's see, let's work on that and see how much he is. So this is 0.16 plus 1 plus 0.64 square rooted, which would be the square root of 1.8, okay, which would work out to be, let's find out, square root of 1.8 on our calculator is about 1.3416. Okay, so let's pause there and we'll pick up on our next video. So we keep these about 10 minutes.